So today, in today's lesson, we will be working on the Gram Schmidt process. Okay. So what this is that when we already learned from the previous chapter that when we can decompose some vector into two orthogonal vectors, then it has a lot of applications in science and engineering, and that makes things so much easy to deal with. So we discussed that in our previous class. But sometimes we have a vector, they are not perpendicular to each other. Okay, we have a set of vectors which is not orthogonal set. So how can we make those vectors orthogonal? Okay, how can we create a set of orthogonal vectors out of non-orthogonal vectors? And that process is called the Gram Schmidt process. Okay, so the idea is this. Suppose, okay, let me just read this here. The Gram Schmidt process is an algorithm for producing an orthogonal basis for any non-zero subspace of Rn given any basis. So we are given a basis, but the basis is not the orthogonal basis. So how can we create orthogonal basis? So the idea is to start with an ordered basis, okay, whatever the basis is given, which is not orthogonal, for a non-zero subspace W of Rn. We then create a new basis out of the old basis iteratively, where each new vector is orthogonal to the preceding vectors, hence also linearly independent from all the preceding vectors. Okay, when this process terminates, we are left with the orthogonal basis for W. Now, what it means is, let's say, you know, what is what exactly is Gram Schmidt process? So it is an algorithm, it is a process, it is a technique that will be able to create orthogonal basis for the space, okay, for this given space, okay, or subspace. Now the idea is this. Suppose we are given a vector, let's say we are given a set of vectors, let's say x1, x2, x3, all the way up to xp, for example. Then let me consider, they are not orthogonal, let's say. Okay, I want to consider two vectors. Let's say this is my x1, vector x1, and this is my vector x2. All right. And now we will create, they are not orthogonal. Now we want to create orthogonal vectors. And let's say the orthogonal vectors are v1, v2, all the way up to vp. That's what we want to create using the Gram Schmidt process. And the idea is to begin with x1. Let us consider that x1 as v1. Okay, x1 and v1 we consider the same. You know, that is the given vector x1. And now we will create orthogonal vectors to x1. In another word, we'll create orthogonal vectors to v1. So what you may want to do is you find the orthogonal projection. Okay, let me just do this. This is your x1, and this vector right here is your orthogonal projection of x2. So we denote that by x2 hat. Okay, this one is your x2 hat. Now, this vector right here is the orthogonal vector to x1, and therefore it is also orthogonal to b1. And how do we do that? Well, I think you already know this one is x2 minus x2 hat, right? So this vector is x2 minus x2 hat. How do we get that? Again, using the same like rule of triangle, because you know, I think we discussed that already before. So this one is x2 minus x0, and we denote that as v2. Now v2 and v1 are orthogonal, and we know what is x2, by the way. We learn x2 is actually the orthogonal projection of x2 onto v1 or x1, v1 or x1, right? That's what it is. This is given by the formula. We already know that this is x2 dot v1 over v1 dot v1, right? That's what it is. x2 hat is given by that. Okay, so now so what we have is that, so we have v1 and x1 are equal, we consider them equal, and v2 is actually x2 minus x hat, right? This is v2, which is perpendicular to v1. So x hat means it is the orthogonal. I think we can write this as projection. We can write this as projection of x2 onto v1. We can write this way too. So this means x2 minus projection of, I'll write this way, x2 minus orthogonal projection of x2 onto v1. That's all we need. So that means x2 minus orthogonal projection of x2 onto v1 is actually x hat. We know that, which means x hat means x2 dot v1. All these are vectors, by the way. Okay, guys, these all are vectors, even if I don't write that vector sign, because we are talking about vectors. So all the time it is vectors, and just keep that in mind. Over, oh, this one is this is v1 here. Sorry guys, this one is, I forgot to write that down here. So x2 dot v1 and b1 dot v1 and v1. So that is the orthogonal projection of x2 onto v1. Okay, so this is what it is. Now, so that means in the figure, that's what we are trying to find. So this basically v2 is this vector right there. So that's what we got. Now, if I want to calculate by the same method, v3, so what I have is that x3 minus orthogonal projection of x3 onto b1 and v2. Now two vectors, okay, b1 and b2. That's what we are looking for. Now, remember, I think we have already discussed that orthogonal vectors, when we have two vectors there, this is how we find. So this means x3 dot v1 over v1 dot v1 v1 plus x3 dot v2 dot v2 v2. So when we have two vectors, this is the formula that we discussed already in the previous section. Okay, all of these are vectors, by the way. Okay, so that means I can write this as x3 minus x3 v1 over b1 v1. Even though I don't write the arrow sign, please understand I'm talking about vector. It's too much work to write this arrow sign all the time. And x3 dot v2 dot v2 and v2. Okay, that's what we got. I want you to continue and find the formula for VP, for example. Okay, continue this V1, V2, V3, all the way up to BP. So that's going to give me, by using the same method, I will have, you see, when there is V3, there is X3, X3, this V1, V1, X3, V2, V2, so V2. So that means, looking at the pattern, what you get is XP, BP will be XP minus XP dot V1 over V1 dot V1, V1 minus XP dot V2, V2 dot V2, V2 minus, all the way it goes, and the last term will be XP dot VP minus 1 over VP minus 1, VP minus 1, and VP minus 1. So this is the formula. This is the formula for Gram Schmidt process. So we're going to use that formula to find the orthogonal basis. Okay. So let's go to example 1. So we are given a space W, which is spanned by two vectors x1 and x2, where x1 is given by this matrix 2, -5, 1, and x2 is 1 column matrix 4, -1, 2. Find an orthonormal basis for W. Okay, orthonormal basis for W. So orthogonal and orthonormal. We'll talk about that later. First, we'll find the orthogonal basis and then orthonormal basis. Okay, solution. Now, first of all, we will check whether this x1, x2 can be basis for W or not. Okay, in order for this to be basis, recall from our previous chapter, it should span the space and the vector there must be linearly independent. Okay, clearly x1 and x2 are linearly independent because they are not multiple of each other and span W. So x1, x2 is the basis for W. Okay, this is the basis for W, no issue there. They are linearly independent as well as they span it is given that W is spanned by these two vectors. Okay, all right. Now it is, but we'll check whether they are orthogonal or not. Okay, but x1, x2 is not an orthogonal basis. Okay, because x1 dot x2 is equals to -5, 1 dot 4, -1, 2 equals is this 0? 2 times 4 plus -5 times -1 plus 1 times 2, which is not equal to 0. So it is not an orthogonal basis. All right. Now what we do is, so we find orthogonal basis by using Gram Schmidt process. Okay, Gram Schmidt process. Okay, so let us create orthogonal. So Gram Schmidt process is v1 equals x1, which is 2, -5, and 1. Now let us create v2. v2 is, according to the formula, x2 minus v1 over v1 dot, sorry, not minus, x2 dot v1. Hold a second. The formula is x2 minus x2 dot v1 over v1 dot v1 v1. That is the formula. So let us calculate this. How much do we get? So x2 is 4, -1, 2 minus x2 is 4, -1, 2 dot v1 is 2, -5, 1 over 2, -5, 1 dot 2, -5, 1 and 2, -5, 1. Okay, so let us calculate this. So that's going to give me 4, -1, 2 minus, on the top, if you do the dot product, so you're going to get 4 times 2 is 8, plus 5 is 13, plus 2 is 15 over 4 plus 25 plus 1, which is 30, and 2, -5, 1. So this gives me 4, -1, 2 minus, it is 1 over 2, and this one, when you subtract that, so you're going to get 1, -5 over 2, then this will be 1 over 2. And if you subtract these two vectors, so the result will be 4 minus 1 is 3, -1 and negative positive 5 over 2 will be 3 over 2. And then this will be 2 minus half is 3 over 2. Okay, this is the vector that we got v2. Okay, now you can check, you can verify whether your answer is right or wrong. Okay, you don't have to show it, but just for fun, just to make sure that you got the correct answer, you can check v1 dot v2, are they orthogonal? So v1 is check. Okay, not needed to show in the exam. We just want to check that our calculation is right. So v1 is 2, -5, 1 dot v2 is 3, 3 over 2 and 3 over 2. So equals, can you check whether this is 0 or not? If it is 0, then that's what we're looking for. If it is not 0, that means we did something, some error there in the process. So clearly it is 0. Okay, so the dot product with 0 means this vector v1 and v2 are orthogonal. Okay, that's important. Hence the orthogonal basis is orthogonal basis of W is v1 and v2. Okay, these are the two vectors, they are orthogonal basis, where v1 is you can write v1 is 2, -5, 1, and v2 is 3, 3 over 2 and 3 over 2. So these are the two orthogonal vectors. Now we need to find the orthonormal basis. Okay, this is step 1. So we found step 1, we found the orthogonal basis. Now in step 2, we'll find the orthonormal. Step 2, to find orthonormal basis, we need to normalize this. Okay, normalization means we need to find the unit vector. We need to normalize. Well, okay, let us just write this. To find the orthonormal basis, basically we find the unit vectors. Okay, unit vector. So to find the unit vector, we already know the idea. V1 So let us find the norm of V1. So norm of V1 will be square root 2 square plus negative 5 square plus 1 square. All we need to do is we need to find the unit vector. And we know that we know how to find the unit vector, right? So we first find the length of the vector, which is now square root 30, and also find the length of vector, another vector V2, which is square root of 3 square plus uh, 3 over 2 square plus 3 over 2 square. And then if you work it out, you're going to get square root 54 divided by 4, which gives me 3 square root 6 over 2. Okay. Now, so orthonormal basis for W is given by V1 over V1 norm. That's how we find the unit vector, right? And then V2 by norm of V2. That's all we need to find. So that means we have V1, 1 over V1 norm is square root 30, and then the V1 is 2, negative 5, 1. And then another vector will be 1 over length of V2 is 3 root 6 over 2. So that 2 will go on the top. So you'll get 2 divided by 3 root 6. And then V2 is 3, 3 over 2, and 3 over 2. That's it. If you want, you can put them together. You can, write this down as this way. You don't have to, but if you want, you can get this 2 over square root 30 and minus 5 over square root 30 and 1 over square root 30 is your first vector. And the second vector is, this will be 2 over 3 cancel out, 2 over square root 6. This will be 1 over square root 6, and this will also be 1 over square root 6. Okay, so this is our orthonormal basis. Okay, any question? Okay, guys, here is another example. Find an orthogonal basis. Okay, I'm just saying orthogonal. If you want, you can find orthonormal later, but let us first find orthogonal basis for column space of A, where the A matrix A is given by this matrix. Okay, and also find orthonormal basis. So I think once you know how to find the orthogonal basis, orthonormal basis is not a big deal. We just normalize it. What it means is we find the length of the vector and we divide the vector by the length, so that we'll get unit vector. So let's look at this first. So clearly the column of A are linearly independent, and you know how to check that linearly independent or not. We discussed that in the previous chapter a lot. So I believe you know how to check whether the vectors are linearly independent or not. Okay, so these vectors are clearly linearly independent and therefore span the column space. The column of this column vector will span the column space of A. But it is easy to see that even though they are the basis for column space, but they are not orthogonal basis because they are not orthogonal. Okay, So column space of A is the span of, let's say this is my x1, x2, and x3. These are the three vectors. So span of x1, x2, x3, where x1 is the first column, x2 is the second column, and x3 is the third column. However, it is, you can verify easily that they are not orthogonal because their dot product is not equal to 0. You can verify that yourself. Okay, so now your job is to create an orthogonal basis for W. All right, guys, I want you to try this on your own. Okay, so first, to create, we use Gram Schmidt process to create orthogonal basis for column space of A. All right, so the formula is V1 equals X1, which means 1, 0, 1, 2. Okay, the first step is that easy. Now, second step, V2 equals, the formula is X2 minus X2 dot V1 over V1 dot V1 V1, which gives me, I want you to calculate this by yourself. I trust that you'll be able to do it. So your X2 is 2143, and then minus your 2143 dot V1 is 1012 over 1012 dot 1012 and 1012. Let me know what is the final vector there, V2. In the same manner, you can create V3. So V3 is X3 minus X3 dot V1 over V1 dot V1 V1 minus X3 dot V2 V2 dot V2 V2. So that is the formula, and so we'll have X3 is, what is X3? 0, 0, 1, 7, and minus 0, 0, 1, 7 dot B1 is 1, 0, 1, 2 over 1, 0, 1, 2 dot 1, 0, 1, 2 minus, and then V1, which is 1, 0, 1, 2 minus X3 dot, so X3 is 0, 0, 1, 7 dot V2. So the V2, I need your help. What is the V2 there? So V2 is, let me just,
2143.
so V2 is 0, second, 0, 1. So many of you in this class got this one, 0, 1, 2, and -1. And since so many of you got the same answer, then I trust that this is the correct answer, because we know that it is very difficult to get the same wrong answer, right? So I trust that this is the right one. And so by, I want to put that vector here, which is 0, 1, 2, -1, and this 0, 1, 2, -1, 0, 1, 2, -1. Okay, and then 0, 1, 2, -1. Okay, I want you to calculate what will be all together and the final V3 vectors. I'll wait for you guys. This is what I got, guys. I want you to verify. Okay, this is -5 over 2, 5 over 6, 1 over 6, and 7 over 6. This is what I got. Please verify if, you know, sometimes I might punch the wrong button, and my calculation may have some error, but you know how to just work with the numbers, right? So yeah. Okay, so many of you got the same answer like mine, so I trust that this is the correct one. And so orthogonal basis, hence orthogonal basis for column space of A is given by B1 and B2, which is B1 is 0, 1, 2, -1, and then another is -5/2, 5/6, 1/6, and 7/6. Now, even though the question doesn't ask us to find the orthonormal basis, then let us find the orthonormal basis just for fun, okay? Also, find orthonormal basis just for fun. All right. Now, okay, so the orthogonal basis for column space of A is not only B1, B2, because there are three vectors. So B1, B2, B3, that's what I was trying to say. And I was checking how many of you are paying attention, and some of you pointed out. That's great. Okay, because there are three vectors. So we'll write V1, V2, V3, which is V1 is this, or V2 is, okay, let me just write it down. V2 is, hold a second. V1 is 0, 1. Okay, this is not V1. So V1 is 1, 0, 1, 2, and V2 is 0, 1, 2, -1, and V3 is -5/2, 5/6, 1/6, and 7/6. So this form the basis for column space of A. Now, you know what? When we want to, we want to find the orthonormal basis, and when we want to orthonormalize, then to normalize it, then we have to do a lot of calculation there, right? Square root and those vectors. So when we have this fraction, okay, when we have this fraction, then calculation is really ugly. In order to make your life easy, what I want to do is I want to, scale these vectors by a factor of 6, okay? Or I can write this as, I scale this, I multiply everything by 6, so that I'll get 6 times -5 is negative 30 divided by 2 will be -15, and this will be 5, and then this will be 1 and 7. By scaling by, we call it scaling by factor, scaling by factor of 6. Do you have to do it? No. But what is the benefit of scaling by factor 6? Now this, earlier you see the vector is really ugly, right? Um, lots of fraction. And now this looks easy to work with when we want to find the normal vectors. Therefore, I suggest that if you want to make your calculation easy, then scale by some factor that will give you a whole number. Okay, so I can write this as, or I can also write this as 1, 0, 1, 2, and this vector v is also a nice vector. I just leave it like that, 2, -1, and but vector 3, I can write that vector as a -15. I multiply everything by 6, so I'm going to get -15 there, and this will be 5, 1, and 7. All right. Now let us find the orthonormal basis. So orthonormal basis means, first of all, you need to find the norm of V1, find it, norm of V2, find that, norm of V3, please find that as well. That's gonna give me Okay, guys, I leave it to you. Okay, v1, norm of v1 is 1 square plus 0 square plus 1 square plus 2 square, which gives me, okay, thank you guys. You already solve it and then put your answer in the chat room. That's great. So many of you got the same answer, like v1 is square root, norm of v1 is square root 6, and norm of v2 is also square root 6, and norm of v3 is square root 300, which can be written as 10 square root 3. Because all of you got the same answer, I trust that this is the correct answer, because it is very difficult to get the same wrong answer, right? So yeah, so orthonormal basis is now, so orthonormal basis for column space of A is given by v1 over norm of v1, v2 over norm of v2, and v3 over norm of v3. All right, so, and we know that this is our v1, this is our v1, v1, v2, v3. So I'll write 1 over square root 6, and the v1 is 1, 0, 1, 2, and 1 over square root 6. v2 is 0, 1, 2, negative 1, and 1 over 10 root 3. v3 is negative 15, 5, 1, 7. That's it. All right. Now, we will, this is all about, finding the orthonormal basis, orthogonal basis, orthonormal basis. And there is one concept that will be working in this section. This is matrix decomposition, or sometimes called factorization. Okay, matrix decomposition or factorization. So if you are given a quadratic equation, let's say x square minus 2x equal to 0, or let's say x square minus 2x is your quadratic equation, and if you want to factorize it, factorize, then you learn that in your middle school or even in high school, that we can write this as x times x minus 2. These are the two factors, right? So what it means is, if you multiply x and then x minus 2, you're going to get that. So these are the two factors, and that's how we already know how to factorize the given expression in algebra. But now, how do we find the factors of matrix? Okay, let's say you are given a matrix A, for example, A, B, C, D. Then, how do you factorize it? What are the factors of matrix A? Well, there are many ways to factorize, many different ways. One way is called the QR factorization. Another method is called the spectral decomposition. Another is LU decomposition, and so many other ways to find the matrix decomposition or matrix factorization. But in this course, what we do is we'll focus our attention on QR factorization and spectral decomposition. And if we have enough time, then we'll work on the LU decomposition as well. Okay, that's what we're gonna do. Now, what is QR factorization? So the process is this. If you want to find the QR factorization of a matrix A, then first you need to find the orthogonal and orthonormal basis of the given matrix exactly the same way that we did in the previous example. Okay, we find the orthogonal and orthonormal basis of A. And I trust that all of you know how to do that. Okay, part A, guys, I trust you that you'll be able to do this by yourself. Find the orthogonal and orthonormal basis for A. So I think I have done it here somewhere. Oh, it's not there. Yes, it is here. So first, B1, recall that the matrix, the matrix A is, so we are given the matrix A, which is 1, 1, 1, 1, and then another column was 0, 1, 1, 1, and another column was 0, 0, 1, 1. This is the matrix given, and we denote them by x1, x2, x3. So using the same Gram Schmidt process, we create orthogonal basis, step 1. So using the same formula, V1 will be x1 right there, and V2 use this formula, and then we'll got this one. But since this is lots of fraction and later on it's difficult to, it's not fun to deal with the calculation of those fractions. So I change it into this simple vector by scaling by a factor of 4. In the same way, you can find V3 using the same formula from Gram Schmidt process, and this is what we got. And again, it looks ugly, so I scale this vector by a factor of 3 to get this. All right, so this is what we already did. And then to find the orthonormal basis, what we did is we found the norm of V1, which is 2, norm of V2, which is square root 12, and norm of V3, which is square root 6. Hence, we have 3 vectors. I denote those normal vectors by u1, u2, u3. So what is this u1? Is basically v1. u1 means, this means v1 over norm of v1. This is your u1, okay, which is this. u2 is actually v2 over norm of v2, and u3 is basically v3 over norm of v3. So we just normalize it, meaning we find the unit vectors. So u1, u2, u3 are all unit vectors. You can verify that by yourself. Okay, the length of the vector u1, u2, u3 will be 1. Now, QR factorization means we need to find, what we need to do is we need to split that A into two matrix Q and R. That's all we need to do. Okay, matrix A is given, and we want to factorize matrix A into two matrix, which is Q and R. We call it QR factorization. Now the question is, what is Q? Okay, listen very carefully. What is Q? Q is a matrix whose columns are these unit vectors, normal unit vectors, u1, u2, u3. Remember, what is Q? Q is a matrix. Q is a matrix with its column with orthonormal columns. Orthonormal columns u1, u2, and u3. So this is called Q matrix. So we already got the Q matrix, which is Q means, the first vector is u1, which is this, u1, u2, u3. Just copy that down. It's that simple to create the Q vectors, because we already know the orthonormal vectors, right? So matrix Q will be just this matrix. Now the question is, what is the R matrix? How do we define? By the way, this Q and R, it is defined in the previous theorem. We'll talk about that later if we have time today. So now what is the R matrix? And R matrix is given by this. Find the R matrix. So R matrix is given by Q transpose A. Okay. From the theorem 12 earlier, A equals QR. So R is basically Q inverse A. But remember, Q inverse A and Q inverse and Q transpose are the same thing in case of orthonormal vectors. Okay, we discussed that earlier in our last class. Just keep this in mind. Maybe we'll talk about that later as well in detail. So R matrix R is given by Q transpose A. So what is Q transpose? Well, Q matrix is already there. So you just transpose that, meaning you change the row into column and column into row. So that's what we got. This is our Q transpose. And then A is this. Okay. Now you multiply these two matrix. If you multiply this two matrix, you know how to multiply it. Okay. Multiply these two matrix and the result will be this one. I trust that everybody know how to multiply the two matrix. Okay, guys, you verify that yourself. Okay, if I make a error in the multiplication, let me know. I think that this is the correct answer, but I want you to verify yourself. Okay, don't trust me just for the first, don't just trust me here in multiplication. I want you to do it by yourself. Okay, that's it. So that means the QR is Q is this matrix, R is this matrix. This is our Q matrix, this is our R matrix. And if you multiply them, you don't have to do that, but you can check your answers, whether it is right or wrong, right? So Q and R, if you multiply them, and again, you know how to multiply the two matrix, I guarantee you that you will get this matrix A. If you don't, that means we made some calculation error. But the idea is, yes, you should get A. Okay, please check this later by yourself. And this is all about a Gram Schmidt process. What we did is we learned how to use the Gram Schmidt process to find the orthogonal basis of the vector. And we also learned how to orthonormalize. And then we also learn a QR factorization of the given matrix. Okay, these are the three main concepts that we discussed in our class today. And this much for today. And in our next class, we'll be working on least square methods. Okay.
Professor?
6.5.